Good day everyone. My name is Gauri Shankar from Electronics and Communication Engineering Department from NIT Andhra Pradesh. I am going to present a course project on optimization techniques. So my project is using stochastic gradient descent for neural network training. The objective of this project is to train a neural network to classify given image of handwritten digits by optimizing the network to make accurate predictions using gradient descent algorithm in back propagation. This gradient descent algorithm is used to optimize the cost function of the training. Firstly, what is a neural network? A neural network is a powerful machine learning architecture that is composed of interconnected nodes which are organized into layers and used to process complex data. These nodes are connected with weighted edges, and also these nodes contain biases which are used for predicting the value in them. And when it comes to the training of neural network, a image is fed into the input layer of the neural network. According to this activation of the input layer and multiplication with these weights, the hidden layer is activated. And according to these activations and multiplication with these activations and weights, the next hidden layer is also activated. And according to these activations, the output layer will be activated. And our desired result is to only activate the corresponding node of this image label, corresponding to this image label. So basically, while training, uh, when we input a image into the neural network, we estimate it to find patterns in this image and decode these patterns and predict the number digit in this image. How to train a neural network? Neural networks are trained using optimization algorithms such as stochastic gradient descent, which we are using in this project, which optimizes the cost function whose parameters are weights of the connections between nodes to find the best combination of weights and biases to a given classification problem, which is in our case classification of the digits. Introduction to stochastic gradient descent. Stochastic gradient descent is a popular optimization algorithm used in machine learning for training neural networks. It is a iterative method that updates the model's parameter based on the gradient of the loss function with respect to other parameters. The stochastic aspect of the stochastic gradient descent comes from the fact that if it is randomly selects a subset of training data, also known as mini batch, means our neural network is not trained on whole data set for each iteration. For every iteration, we are selecting a mini batch of data set to train the network, and then use our stochastic gradient descent algorithm in back propagation, and then we tune the weights and biases according to the cost obtained. Okay, intuition of gradient descent. Firstly, let us assume we are using a cost function of only one variable, that is only one weight. Okay. Let us consider our cost function is like this, and we initialize our weight to be a random one. We find the gradient of this point, and then we move the point to the new location according to the gradient and learning rate. We do this process iteratively until we reach or we converge to a local minima. let, Now let us assume our cost function is of two variables, so that is our cost function is of two dimensions, and here also the same thing happens. Our optimization algorithm converges the cost function to a local minima. That is, it finds the best combination of weights and biases to converge the cost function to a minima. Basic implementation of gradient descent. Well, our we are using gradient descent to optimize the cost function of the learning, right? We are using the cost function root mean square. No, mean mean square mean square cost function, where in this is the formula for the finding the cost function. Here x denotes the input vector of the neural network, h of x denotes the prediction of the neural network according to the input, and y denotes the label that is actual desired output of the neural network, and m is the size of the input vector. This is sample code of gradient descent in Python. Our gradient descent takes the parameters like gradient, which is a derivative of the cost function, with respect to different parameters like weights and biases, starting point, learning rate, and n iteration. And that means the number of iterations we desire the gradient descent to run. Okay, we start the vector at the random point, and then start our gradient descent algorithm for n iterations, and then we we update the start vector according to the difference value. This difference value is calculated by this one learning rate times the gradient vector, and then we will finally return the vector, updated vector. This is a optimized one of optimized version of gradient descent function, which we have seen in the last slide. In this one we have introduced a new parameter called tolerance. That means if during this n iterations, if we reach a desirable tolerance value, then we will stop the training of the neural network before it even completes the n iterations. Implementation of gradient descent. We are using a training neural network model of which contains 784 input nodes, two hidden layers of 16 16 nodes each, and 10 output nodes. Each node is connected to each node in the next layer. That means each node in the previous layer is connected to each node in the next layer through weighted edges. These are the weighted edges. Okay, and each node contains biases. All the weights and biases of the network are initialized randomly. An image is fed into the input layer, and the network makes a prediction out of it. Here, the image is nothing but a matrix of 28 by 28 size, and we are reshaping the matrix into 784 by 1. And we are feeding this image into the input layer, and the network makes a prediction out of it. And as expected, the output will be useless in the initial stage of the training. The cost of this prediction is then calculated. The gradient of cost is calculated in the back propagation. Parameters are upgraded according to the gradient descent. See here, we are calculating the gradient, and then we are updating the weights and biases of the network according to the obtained gradient, and the learning rate we have set initially. And steps 2 to 5 are repeated. Means we will repeat the steps like inputting a image, and then finding the cost of the predicted value, and then again finding the gradient of the prediction, and then tuning the weights and biases, and then again inputting a image, and this will be done for n iterations, and these iterations are also called epochs. See, this is the desired behavior of our neural network. If we input image like this one, 4, our neural network is desired to give the output as output like this. That means our output node of index 4 should be of higher value compared to our remaining nodes. But in the initial stages of the training, our neural network will not give the desired output, and it but it will give some random outputs like this. But our task is to find the cost of these two values, and then we use the stochastic gradient descent to update the weights here according to the cost. Mathematics of the gradient descent will be discussed in the coming slides. Limitations of gradient descent. Despite its success, stochastic gradient descent still has some limitations that need to be addressed. For example, it can be sensitive to initial values of the parameters, the choice of hyperparameters such as the learning rate and mini batch size. Additionally, it may not be well suited for non-convex optimization problems where the loss function has multiple local minima. We will see what that means. We will consider a cost function of one variable. If we initialize initialize our or starting point like at this point, it will converge to minima like this. But there are many possible ways of initializing this value, like this initial value may be here. If we initialize the value here, then the minima will be converged to this one, not this one. But if we initialize to this value, then the minima will be converged to, then the cost function will be converged to this minima, not this minima. So each time there is a potential risk of getting different minimas if we initialize the random value at random position of the on the cost function like this. And if we come to the limitations of our model, we can train our model to detect the digit in our input image. But if we give the input of random pixel values to the network, then it will give some prediction, but not if we consider our neural network to be intelligent, it will give like this is not this image does not contain any number, so I can't find any number or lighting up of multiple nodes at the same time. But it will not behave like this. It will show some confident value if we input a random image, then it will confidently lights up or activates some node. So this is one of the limitations of this basic multi-layer perceptron network. When we look at the algorithm of the gradient descent, we initially initialize the weights and biases of the network, and then we start the training of the neural network by giving input image to the network and then finding the cost of the output. Finding the cost means the difference between the output predicted output and the desired output, and then we find the gradient of the cost and update the weights and biases according to the gradient. Here the alpha is the learning rate. These are the steps involved in training the neural network. In forward propagation, the input data is fed into the neural network and the activation of each layer are computed using the current values of the weights and biases. The equation for this forward propagation is shown here. Here the activations of the layer is computed according to the weights and biases of the previous layer. Computation of loss. The difference between the predicted output and the ground truth is qualified by loss function, which measures the error of the network on the current batch of data. Loss function, it is basically computing the difference between mm, square of the difference between predicted output and the desired output. In backward propagation, we are finding the gradient of the loss function with respect to each weight and bias. That means how the cost function will vary if we vary the respect to weight by how much. Okay. Using chain rule of calculus, this involves propagating the error signal backwards through the layers of network and computing the derivative of each activation function. And according to this gradient we obtained in backward propagation, we will update the weights and biases of the network. We will repeat the process 1 to 4 iteratively and until a fixed number of iterations or until we reach desired accuracy or tolerance. I- In this, we are using functions like um, relu, which means if the value in this function, if the value of x is less than 0, it will just give 0. If the value of x is greater than 0, that means the x is positive. Then only the function value will be x. And we are using the softmax function for finding the values of the output layer. This is the softmax function. These are the equations for forward propagation, and these are the equations for backward propagation using the chain rule of calculus. Means we are finding the derivative of cost function with respect to weights and biases. And after that, we are updating the weights and biases in each layer according to the gradients we obtained in the backward propagation. See, these are the gradients we obtained in the backward propagation, and according to these gradients, we are updating the weights and biases. Like this way, I have trained a neural network for 1500 iterations with a learning rate of 0.65, and I achieved maximum accuracy of 95.7 percentage in on training data. But when I tested it on the test data, that means this test data is nothing but data which is not included in the training data. That means test data is entirely a new data which is shown to the neural network for making predictions, and the neural network is 94%, almost 94% accurate about the predictions. And as we discussed, the drawbacks of this network is stochastic gradient descent might converge to a local minima uh, according to the initial values of the weights and biases set set to the network. And the second drawback is the if network is fed with an image with no digit and some random values of pixel data spread here and there, then it will gives a confident prediction of a number. Now, if we see the source code of this project, we have used libraries like NumPy, Panda, Matplotlib, and for data processing and data acquiring from the datasets like train.csv, which are located in my local computer. In this block, we are just dividing the data set into training data and testing data, in which like our total data set has a total of 42,000 images, image data, 42,000 image data, and we are splitting this 42,000 images into 40,000 of test training data and 2,000 of test data, 2,000 images of test data. Okay, see, we can see that these are the label values for the training data. This is the function for initializing the parameters like weights and biases in each layer and between each layers. This is the relu function we have used. This is the software function we have used for output layer. In this is nothing but forward propagation. This function does the forward propagation function. This is backward propagation, which basically implements the equations we have discussed in the report. And this function just updates the parameters based on the gradient obtained in the backward propagation. See, this backward propagation will return the values of all the gradients with respect to weights and biases. And this is the training of our model, and I have trained this model for 1500 iterations and with a learning rate of 0.65, and I have for this training I have achieved an accuracy of 95.605. 95.6 percentage. And when I tested this model on test data, it is 94.45% accurate. Now I will be using these images For to test the network whether it gives the actual predictions or not, let us look at these numbers, images actually. See, these are the images of these are highly pixelated because these are of very low resolution. This is a image of 0, 1, 2, 3, and so on. Okay, and we will be feeding these images into the neural network and see whether it gives actual predictions or not. All this snippet does is it reads a data, it reads a image from the specified path, and then resizes this image into 28 by 28 pixels. So if it is not a 28 by 28 pixels size, and our image is of 28 by 28 pixels, so there is no need to resize this image, but this is only for reconfirmation. The images of 28 by 28 pixels, and then we get the array of this 28 by 28 matrix, and then we normalize all the values in this matrix. This matrix contains values from 0 to 255. We normalize these values between 0 and 1. Okay, and then we reshape this matrix from 28 by 28 into 784 by 1, so that we can feed this image into the neural network, and then we give this array into the model, and then look at the predictions. Now let us give the number of 2, like image of 2. Okay, if we run it, we can see that it actually predicted the number in the image is 2. Now we check on the number 7. 7, see, it predicted the number as 7. Like this model is actually predicting, and the accuracy of this model is pretty high, so it will almost predict correctly of our images. To summarize this project presentation, a neural network is trained by setting specific weights and biases. Weights of edges and biases of nodes are parameters to be tuned. That is, these parameters are the inputs to the cost function, and we are using the stochastic gradient stochastic gradient descent to find the gradient of the cost function with respect to these parameters. Gradient descent iteratively optimizes the parameters to minimize the cost function. Cost function is the mean square of the difference between actual value and prediction value by the neural network. If the dataset the neural network is being trained on is very large, subset of the dataset is selected randomly for training in each iteration, which is stochastic gradient descent. These are the references I have used for this project, and sh- uh, snippets of the pictures I have taken from the YouTube channel 3 Blue 1 Brown. Thank you.